Hello, so the purpose of this video is to explain the pendulum clock and the spring scale activity. To do that, you're going to want to be aware of these two equations here. These are in the slideshow that was in the same day. Hooke's law, F equals negative K times X. And then T equals 2 pi square root of L over G. When you do these equations, please note, G is always going to be 9.8. And this is the period of the pendulum, which represents down and back. That's kind of a big deal. And then also down here, this negative confuses some people. If that does, you can just forget about the negative if it really bothers you. It has to do with direction of forces. So on the stopwatch timer with the pendulum, of course you can do just a regular stopwatch and you can time an event. Say the time takes for someone to run a lap around the track or run 100 yards or something like that, and you could get a really accurate time. But if you happen to be in a situation where you had an evil physics teacher who said you can't use a stopwatch, the only equipment that you're allowed to use is some string, something kind of heavy, and an equation. You know, you can use a calculator too to kind of solve things. Could you use that to time it? And in fact, you could, because I should add, you also need something like a meter stick to measure distance. But if you know the distance of the pendulum, in other words, if you know the distance from right here, it'd be the center of mass, up to the pivot point, then you could just simply count 1, 2, 3, 4, 5. That would be 5 periods. You could actually solve for the time that it takes to go down and back, and if you did it 5 times, assuming you knew length. So you're going to have to know the length of the pendulum. So the idea of this activity is basically make a stopwatch out of a pendulum that you could accurately time using this. And the secret is, don't start by making a pendulum. Start by thinking, what's an even number that I can make T, or this round trip distance? What's an even number that I can make that? And solve for L. In other words, what could you, this would be easy to keep track of time with. And that's all I'm really going to say for this, the pendulum clock part of it. Okay, so we've jumped ahead to the second part of this activity, part 2, which involves finding the weight of some mystery bag. And for I have all kinds of different mystery bags. In this case, we'll just say these bag of these 2 doom buggies. Question is, how much does this weigh? And the first thing you want to remember is a couple common units of weight. Remember this would be something like newtons or pounds. And since this is the SI unit, remember weight is in newtons. Weight is a force. And so towards that end, of course, you could use something like this to find the mass, or probably convert it to weight with your, this tends to spit it out in terms of mass, which is not in unit of weight, which is annoying. But you also could use something like this that we already know an established mass. In this case, this is a 500 gram mass. And then we're going to use this equation here, and we can use this spring in place of this using what's known as Hooke's law. And the way this would work is, first we need to establish, you have to know 2 of 3 things to solve any equation like this, right? So right now, we don't know any of these for this spring. So the first step would be to establish what is K for this spring. And to do that, we would need to take a known force and a known distance to solve for K. And that would be the first step. And the way you would do that is you would take something that has a known force. Since this is 500 grams, this would be 0.5 kilograms times 9.8, which is G, and then we would get 4.9 newtons. So anytime you take the mass in kilograms, multiply it times 9.8, which is acceleration due to gravity in SI units, and that would get you in newtons. So in this case, our force, and I'm going to put a little mark here, this is the spring at rest. Our force in this case is going to be 4.9 newtons. Okay? Now, we still don't know K. But we could find X, because remember, the spring moved from here. This would be X, is this distance, which I could get it. It's going to be 16 centimeters, which is equal to 0.16 meters. But remember, everything should be in SI units, because SI units for force, SI units for distance. So then that would be 0.16 meters. And in this case, we could solve for K by taking, dividing both sides by, divide both sides by 0.16. All right, and so that would be 30.6 newtons per meter equals, that would have been negative, equals a negative K. Again, if the K confuses you, you can just cancel that out. But now, and I'm not actually going to do this in my example, but now what you could do is you could take this spring, now that we've established its K constant, its elastic constant, which is K, you could put this in your pocket and take it to Europe, and you would have yourself a faithful way to weigh things, because that K doesn't change as long as you're within the elastic limits of the material. So we could take this and we could measure the, once again, we could measure the weight of this mystery bag. And so in my case, I already have my starting point. I would have a new displacement, so I could find a new X for the mystery bag. Then I would use my same equation, F equals negative K times X. I have a new X. My K, negative K, is already established. And so then I can solve for F and get my mystery weight. Thank you. And thanks to Nolan Anderson for filming this. Have a great day.